My name is Nicole White. I am a data scientist at Neo4j. And in this session, I'm going to be talking about data science and recommendations. So my background with Neo4j is I've been with Neo4j for about 2 years now. And I've been working with Neo4j and Cypher for about 3 years now. I discovered Neo4j when I was in grad school, working on a lot of social networking type problems. I went to grad school in Texas at UT Austin, where I got a master's in statistics. And then before that, I was in Louisiana getting an undergrad degree in math and economics. And now I'm working in San Francisco at the headquarters for Neo4j. So recommendations are probably the most common use case for Neo4j. And it's definitely the use case we use in marketing and sales to explain why Neo4j is so powerful and easy to use. And then we're also going to do a very, I would say, tiny amount of quote-unquote data science, where we're going to show how to incorporate some more statistical methods into some recommendations. So the agenda for this session is, first we're going to look at the example data set that we're going to be using for all the examples that we're going to go through. I'll talk about the data model so that we're all on the same page. And then we're going to go through some different recommendations, and they'll get a bit more involved as we go. We'll start with a really simple one. It'll just be Cypher. And then we're going to get into a social recommendation where, again, it'll just be Cypher, but we'll start taking social aspects into account into our recommendation. Then we'll look at a similarity recommendation. This is referring to similarity metrics that you can calculate. There's tons of similarity metrics. I just chosen one, and we'll do an example with that. And then we'll do a clustering recommendation, where we'll do some graph clustering and then do recommendations based on people being in similar clusters to you. So they'll get a bit more complicated with each step. So let's look at the data set. The data set is places, these food and drink places, in Dallas-Fort Worth Airport. This might be the wrong audience, but have any of you flown through Dallas-Fort Worth Airport in Texas? Okay, maybe some Americans. It's a major hub in the middle of the United States in Texas. A lot of flights go through it. So this airport, of course, has lots of bars, restaurants, shops. And in this data set, it's pretty small, but we have these place nodes in the yellow. So we have a place label. These are place nodes. And we have a part of our model, thanks, this ended up working, modeling which gate they're at, which terminal they're in. And then we also have categories that these places are in. We have, Mexican food, sandwich, there's bars, barbecue, all the major categories for food and drink. So let's do a simple recommendation. This is the classic, you probably hear this in most Neo4j spiels, which is, find me places in the following categories closest to gate whatever in terminal. This is something that you could potentially type into Facebook, right? In this scenario, we're going to pretend that these black, bold, curly brace name things are like user inputs. So hypothetically, we have an app. Users are inputting variables or parameters that they want these recommendations on. And this will map, this English sentence will end up mapping very nicely to a Cypher query. So let's look at this Cypher query that will accomplish the recommendation we just requested, which will match at a place that's in some category, that's at some gate in some terminal. Hopefully, everyone's seen a little bit of Cypher already. I can't really go through the details of the syntax of Cypher, but long story short, we're getting all the places in their categories, their gates and the terminals, where the name of that category is in whichever categories the user requested, and the name of the terminal is whichever terminal the user said that they were in. Then we're getting all these things, the absolute distance of the gate of the place from the gate that the user said that they're at, because presumably they don't care if they have to walk left or if they have to walk right. They just want to walk the minimum amount of distance to this place. Order by that, ascending and return these places. So we just recommended a very simple recommendation to a user based on just their location in the airport. And Cypher makes that very simple. Let's look at a social recommendation. So let's say our app also has users, our hypothetical app. We have users who can log in and like places, very, very similar to how you can like things on Facebook, right, or check into places. So let's say we also have users. This is another label in the graph. And they have likes relationships to a place node if they have liked the place. And let's also pretend that users can be friends with other users. And that's modeled by a friends with relationship between user-labeled nodes. So consider this on top of the other model that we already explored. And now let's find food and drink places in the following categories, closest to gate in whatever terminal, that users' friends like, because presumably you will like things that your friends will like. So we're going to take this into account in our query. So match clause is pretty similar up to a certain point, except now we are matching on places. So these first three lines are the same. But for the user in question, the user that's quote unquote logged in, we want to find their friends through this friends with relationship. And we're leaving the direction off because we don't care which way it is. We're getting their friends, and then we're getting the places that their friends like. So we're only getting places here. This P is referring to the same variable up here, where that user's friend has a likes relationship to that place, right? So now we're taking a social aspect into account now very easily with Cypher just by adding a few more lines. And all the same stuff here where we want to assert that the category, we're only showing them categories that they explicitly asked for in the terminal that they're in. And of course, we want to filter this by the user who is logged in and making this request, right? And then similar stuff here, we're getting the name of the place, its location, its category. We're counting how many of their friends have liked that place, and getting, again, the absolute value of the distance of the gate, just to show them how long they're going to have to walk to this place. So just a few more additions to this query, and suddenly we have added a social aspect to our recommendation. And we're returning it here in the return clause. All right, so let's look at a similarity recommendation. So looking closer at this data model, this is the same thing I showed earlier, where we have users who can like places, and let's say that they can also rate that place with an integer 1 through 10, for example. So they can like a place, but they can also say, well, I liked it this much with some number weight. And in E4J, that can be easily modeled by a property on the relationship. In E4J, you can put properties on both nodes and relationships, which makes modeling very simple. So we have these weights on these likes relationships. And so we can find how similar users are to other users by looking at this, for example. There's lots of ways you could potentially do this. But this is the way I've chosen to do it in this example. So remember we have users liking places with these weights. And so we can determine how similar any pair of users are. In this example, we have Greta and we have Alice. And we've queried the places that they've mutually liked. And then for each of those places, we can see the weight which they've given that place, right? And presumably, we'd be able to take this information, these numbers, and determine how similar they are to each other. So like all of data science, people are reduced to numbers, right? So here we have Greta and Alice reduced to 2 vectors of numbers. These are their ratings for those places, in the correct order so that they match together. So here we have 2 length in vectors. And there are tons of similarity metrics. You can go, there's a Wikipedia page of all of them. I've just chosen Euclidean distance because it's very easy. We all learned it probably in grade school to find the distance between 2 points on a plane. But you can do this with any dimension of vector, not just two-dimensional vectors. So let's get the Euclidean distance between these two vectors of numbers, or rather these two users, which is just the square root of the sum of their squared distances. So this is a Euclidean distance. Plugging those numbers in, the 795, the 931, gives us this similarity. I guess it's technically a distance metric between them. But you can do this pretty easily in Cypher, right? You can do this between two specific users on the fly very quickly, especially if they've only mutually liked a small subset of places, right? So here we're matching on a user Alice. So here we have U1 and U2 variables where the name of that user is Alice and the name of that other user is Greta. And we're finding places that they've mutually liked. So here they both have to have a likes relationship to the place for it to be found in this result. And that's pretty much the query I wrote to show you the picture of them mutually liking places, right? And then we can easily calculate the Euclidean distance between them with the square root of the sum of their square differences, right? Because there's that weight property on each of these likes relationships. And here we get the same answer, right? Except we did it in Cypher. The problem, though, is that it's easy to do this between two specific people, but if you're trying to do this in real time, and you have, hypothetically, again, you have a user logged in, and then you're trying to you're trying to infer their similar users on the fly, you're going to have to compare them against every single user in the database in real time, which might not work out so well. So what I've done in practice is to pre-compute this and store it in an actual relationship. Obviously, in large data sets, you would do this in batches. But in this little example set, I can match on a Cartesian product, more or less, of all the users and the places they've mutually liked. So all users, places they've liked together. This is just a trick to ensure you're not finding the same pair twice on both the left and the right. Then with their Euclidean distance and themselves, we're going to create a relationship between them, called distance, I suppose, and set a Euclidean property on it called Euclidean. And hypothetically, you could also store other similarity metrics on some relationship between users to capture different similarity metrics, because some might be more useful than others in certain contexts. So again, the ability to model properties on relationships in Neo4j makes stuff like this very easy. And in practice, you probably don't want to store every single relationship that can possibly exist, because in practice, you probably only want to return the top few people, right, of their top, in nearest neighbors. So you can just store the top in according to some threshold, so you don't have this fully connected graph. So there are a few considerations to make when you consider this type of modeling. But in essence, this has been found to work roughly pretty well, because then you can do queries like this in real time, where we want to find places in the following categories, close to some gate and some terminal, that users similar to the logged in user likes. And in this way, we don't have to compute the similarity on the fly. We've pre-computed it and stored it on a relationship, and in Cypher, we're able to grab that very quickly. So here, we're matching on places and categories. Again, these three lines are the same, except down here, for the logged in user, for you, we're getting users who have a distance relationship to them, and this is where what I mentioned comes into play, where in practice you should probably only store the top in relationships to users who are similar to them, so you're not grabbing so many users in this match, but we're grabbing users who have a distance relationship to them where those users like that place. So here we've been able to express a somewhat complicated pattern in just a few lines. And we're also grabbing that likes relationship and putting it on a variable because we're going to use those weights later to give them a rating, more or less. And where clause is the same here. We're going to assert it's in some category. But what's important here is that we're ordering those users by their distance, ascending, because it is a distance metric, and we want the lowest ones. The lowest distance is the most similar. And then with those other users ordered by their Euclidean distance, we're going to collect the top 3 users' ratings as ratings, and we're going to use that as our just average score to recommend these places. So I guess in English, we've taken a user who's logged in, and we've found users who are most similar to them, places that they've liked, and then average the scores that those similar users have given those places to rank those places in this result set, right? So there we're getting the name of the place. We're essentially taking an average here. We're just adding it up and dividing by the number of elements in the collection. And we're ordering by that average descending. We're then secondary, we're ordering by the gate distance. Hypothetically, there could be ties, I suppose, and then you order by the gate distance, and then returning the name, category, gate, terminal. All right, let's look finally at what I'm going to call a clustering recommendation. But in general, this can be thought of just as offline, the whole workflow of offline computing of similarity, of clustering, of what have you, that people find themselves doing quite often because there are a lot of things that Cypher just isn't, it can't do. That's probably been made obsolete now by the procedures that were announced earlier today, so maybe these slides are irrelevant now, but sometimes you have to do these algorithmic approaches that currently Cypher doesn't expose, at least in 2.3. So this is what I've always had to do, which is use some form of statistical software, pull data out of Neo4j into, let's say, Spark, R, or Python. Here I have an example of some R code. You don't need to know R. Just think of it as pseudocode for pulling data out of Neo4j, running some algorithm, and then, if appropriate, writing the results of that algorithm back into Neo4j as either a property, a new node in relationship, or maybe a new label. And by persisting the results of that algorithm in the graph, you can use it in real time with queries that are similar to what we've just been doing. So here I have some example code with how you do this in R. You could easily do the same thing in Python or Spark or whatever you're most comfortable with, but essentially log in, connect to the graph. In this example, I've decided to cluster users together by their similarities. I could have clustered by their Euclidean distance that we showed earlier. That was one option, but you're really open to do whatever features you can infer. So here I've decided to represent each user as an observation, and I want to get the average rating that they've given each category. Presumably, users who rate the bar category in very similar ways are just similar in general. So here I'm grabbing users who like places in some category, grabbing the name of that user, the category name, and the average weight of the likes relationships as average weight. And that's going to give me a table like this. And then through some data manipulation, like I said, I eventually want each user to be an observation where each feature is the average, weight, rating they've given restaurants within that category per category, and these are their features. And I'm going to use this to determine how similar they are, and I'm going to use a clustering algorithm to determine users being in different clusters. So in R, this is really easy. I've decided to use k-means. There's several clustering algorithms. It's just one I chose for demonstration purposes. So you can easily grab the cluster assignments out of this. And we're going to go ahead and get their cluster assignments. So long story short, I ran a clustering algorithm. And now for each user, I have a cluster assignment. So Bob and David are in the same cluster. They're in cluster 2. And this will allow me to see in real time which users have been determined to be in the same cluster, which is a bit more, in some contexts, is a bit more enlightening than simple just distance, because clustering will, I guess it will minimize the within cluster variance. So I've then written that to a CSV. And then I can load this into the graph, right? So again, I had users, and I had cluster assignments. And so this CSV just has 2 columns. So I don't know if you guys have seen load CSV before, but it's a tool we've built into Cypher, or I guess a syntax we've built into Cypher, where you can call a CSV from some file path or file URL, and alias it as something, and then we're going to match on the users that already exist in the graph. We're going to grab the user column out of that CSV. We're going to merge on the cluster. Here we're creating a new labeled node in the graph. This is a new label with some ID, the cluster ID, because they all got an integer ID. That was what k-means did. And then we're going to create these relationships between the user and the cluster, saying this user is in this cluster. And then we'll be able to easily query, when we get to the actual recommendation, users who are in the same cluster. So now, as was shown, we now have a new label cluster where users who are in the same cluster have a relationship to that cluster. Right? So this is where our data model is now. And of course, you'll also have to imagine that there's the friends with relationships and likes, and this is all on top of the data model we've already looked at. So now, let's look at considering food and drink places in the following categories, closest to some gate in some terminal, that users in that user's cluster like. So now we've gone beyond just users similar to that user, but users who are in the same cluster as that user. And presumably at this point, we've deleted those distance relationships because we've gone this route instead. Right, so again, 3 lines are pretty much the same, but now we've taken the user who's logged in. We're getting which cluster they're in with their user cluster relationship, and we're getting their neighbors in that cluster who are in that same cluster. So we've assigned that to some variable CL. Then we're getting other users, which I've aliased as a neighbor variable, who have a user cluster relationship to that same cluster. And then we're getting the places that neighbor has liked. And again, we're putting that likes on a variable R, because we're going to want to be grabbing those weights off of the relationship to order our results once again. So this query should look pretty similar now. All we've really changed is that instead of using the similarity distance or the distance metric on that relationship, we're now grabbing users in the same cluster, asserting categories, asserting the terminal, asserting that we're only grabbing the user who's logged in. We're collecting all those weights of the likes relationships from their neighbors liking places. Again, this is just taking the average of that collection. And then we're getting the category, again, the absolute value of the distance, ordering by that descending, and returning those results. So we've been able to take a pretty involved process and persist it in the graph, and then use the results of that algorithm, the results of the clustering algorithm and the clustering assignments in real time. And the workflow that we've found to work out pretty well is to just update these clustering assignments, however often you see fit, nightly, every hour, what have you. And of course, you can use intuition to figure out, how often is acceptable to be updating these cluster assignments. I don't think we have time for questions, but it's exactly 4:15. But thanks, everybody. I'll be outside, though, if you want to talk about any of this.